hear me clearly? No? Yeah, I know it's maybe it's closer. Okay, good afternoon. I will make it fast, I hope. You probably noticed from David's presentation yesterday that he proposed I should do some work for Eminate, and he proposed a few years ago. I was still young at that time. Sorry. So I said, okay, I would love to do some work. No, I'm getting a little bit tired after, so many processes. This work still, this agreement still hasn't finalized yet. So Eric will lead the group to review the approach. So that's why I put the title as a proposed approach, estimating speciated mercury adaptation for Eminate. Okay, I mentioned this before, yesterday. One of the major goals of the Eminate is to provide dry adaptation estimation with reasonable accuracy, of course. We can only do what we can. I should caution you that even for the most studied inorganic species such as ozone and SO2, the most commonly used dry adaptation scheme, like US EPA and Canadian CAPMA and the European schemes, like I was involved in 3 separate dry adaptation model in the comparison, like one with the US group, one with European, one with China, who actually used the American data. All the study shows that the uncertainty on monthly or even annual average is still as large as a factor of 2 for the flux or deposition velocity estimate, even for ozone as SO2 nitric acid gas. Those species are mostly studied. For the mercury, we don't even know what we measured, as you have seen from the past 2 days. We don't even know if the surrogate surface are measuring the dry adaptation or it's definitely not the actual dry adaptation, because the leaf surface, the stomata soil, definitely are different from the surrogate surface, and the turbulence also different. Even though you put you collect inside the forest or over the grassland, everything are different from the real dry adaptation process. So the measurements have large uncertainties. The models have large uncertainties. But from the, we use the best knowledge we have, and use all the data we can find, and I think this is the best approach so far available. Okay, I should go quick here. So Eminate has 2 4-hourly data. You know that it has 3 forms. What I proposed are 3 different schemes for 3 forms of mercury species. One is the first one is the big leaf gaseous dry adaptation model for GOM, a bulk particle dry adaptation model for PBM, a bidirectional surface exchange model for GM. And we have archived forecasted surface meteorological data since 1997 for dry adaptation purpose, because as early as 1997, my supervisor at that time, who was Jeffrey Brook, we had a view of providing dry adaptation estimation over the whole North America. So Canadian forecast model, I think, is a very good one. It has nested grid, it has high resolution over North America, and rough grids outside North America. So it's a global model, forecast model. So land use data, we can either get it from on-site observation or from remote sensing. That's easy. Okay. For GOM, this big leaf model was originally developed for around 30 gaseous species, mostly inorganic, a few organic species. It is for Canadian air quality model. Then in 2009, a review paper on mercury adaptation. When I first worked on mercury, I reviewed all the available deposition velocity for GOM, PBM, and GM. So I proposed some parameter, which you probably saw from Joyanne's presentation just an hour ago. So the alpha, beta are two scaling parameters. I wouldn't go to details. Then later on, when I use the LIT4 data, MNet data, everything put together and calculate everything, I found that like alpha, beta should be 10. So that's paper in 2012. I think that's the best mercury dry deposition estimation so far, because we use the LIT4 measurements to constrain the dry deposition estimation using this big leaf scheme. And this model has been widely used in chemical transfer models and by a few groups as early as IES touched mercury. Okay, so I won't go to details of this of the mathematical formula of that one. So for PBM, originally, like in that paper, I used my size resolved particle dry deposition model because this is the most widely used model worldwide. And it's been evaluated, in different way, like comparison with a review of measurements and compared with size resolved measurements or bulk measurements. I think it's reasonable for dry deposition estimation. But MNet only collect PM2.5. And I think for ecosystem study purpose, they need the total dry deposition, not just PM2.5. Also, from a collaboration I had with a Taiwan group who collected the mercury and metal dry deposition data, I found that if you have a knowledge on mass fraction of PM2.5, PM2.10, and 10 plus, if you have a fraction of this three size range, even though you don't have a detailed size distribution, you could get the same accuracy as using this detailed size distribution. So because of that knowledge gained from that study, and because of the monitoring networks only collect the bulk PM2.5 or bulk PM, I think it's convenient to further extend this model to the bulk ones. So I propose to use this one for MNet. Okay. So this is the original scheme. This formula applies to both bulk model and size result model. I propose to parameterize the surface deposition velocity. This formula is for PM2.5, this is for PM2.5 and 10. Okay, there are two types of land use category. One is with constant land use categories, and another one with variable leaf area index, like for deciduous forest, the leaf area index changes with the year. So there's an additional term. I'm not showing how I got this, but the comparison result is that this model produces the same results as the original size result one. So if we use this one, so the deposition velocity for fine particle times the MNet made concentration, you get the flux for fine particle. That's the monitored flux currently in the MNet approach. And if you have a knowledge on the cost fraction of the particle, or you could assume, let's say, 30% would be a reasonable assumption for cross particles. Let's say for mercury species, it is 30% mercury, particulate mercury in cost fraction. Then you have a deposition velocity for fine particle, deposition velocity for coarse particle. Then you can estimate the total. So that's why I propose to use this approach, because we can provide two numbers. One is the actual measured one, the other one is the total, including the missed one. Okay, for GM, as I mentioned in this paper, I used, again, the same big leaf model, but different parameter, of course, for GM to calculate the hourly dry deposition, then add together to get the annual one, then use the chemical transfer model generated annual, natural, and re-emission to get the net deposition. So this is net GM. So for that approach, you can only give you the annual number for the net dry deposition. Also, I'd like to quickly mention that the net deposition is about half of the total dry deposition regionally. For some sites, for some remote sites, like I remember there's one Kajimukuji, is it AS01? Okay, see emission is very low, so the dry deposition would be very high. For some industrial or urban sites, the emission is higher than the net dry deposition would be low. Anyway, so the original approach only give you an annual number, but this is a bidirectional approach. So if you do not assume the bidirectional exchange, it'll be all the deposition is just one unidirectional flux, like go to stomach, go to cuticle, and go to soil. And if you assume that it's bidirectional exchange between stomach and air and between soil and air, then your formula changes. You need the concentration gradient from the reference height and at canopy height. This canopy height, you don't need to measure that. It's a middle variable, which can be calculated based on the three passes. Okay, this is final, it's the final formula, but you need some mathematical process to get that one. Then how do we get that? Two parameters are needed for this bidirectional. That's emission potential from soil and from stomach. So we did some literature review. We found that the bidirectional exchange are dependent on all these factors, such as soil mercury content, air concentration of the mercury of our gem, canopy wetness, and atmospheric. I mentioned that and other stuff. But if that model, we can handle most of this except the canopy growth stage, because we haven't included that yet. Apparently, the data shows that at the spring, if the new leaf grows out, there's little mercury inside the leaf. The bidirectional, the emission is very low. Emission potential is low. But in the fall, once the leaf accumulates a large amount inside the leaf, then the emission potential is high. We haven't considered that. But all the other factors are basically in the model. So we did lots of sensitivity tests for all the most available emitter sites which we have data. And we tested emission potential from soil, emission potential from stomach. Then we can calculate the canopy compensation point as a function of these two parameters and compare with literature reviewed results. And then we choose the most appropriate value for each individual eminent site. These are results. The original one on the left, that's the original net dry deposition shown in the 2012 paper. And use a bidirectional approach, we get very close results at most of the sites. There's one that has a large difference. I believe this is probably on the middle North America, in the middle region, the middle USA probably. Maybe because the leaf index, the default value of leaf index usually in the model may be too large. If you use a small one, you could probably will bring this down and get closer. So some on-site measurement might be helpful. The advantage of this new approach is that, as I just mentioned, all the approach only give you annual number, but the new approach can give you 2-hourly value. This is just an example. All the value, just dry deposition without extracting subtracting the emission. This new model would show you some emission during the hot summer days. Okay, that's it. The next step would be waiting for the approval, then I can start working. Any questions? Go ahead. Oh, okay. Yes, yes.
Very quickly, because I also do similar type of calculation, would you comment on those parameters that we have a little knowledge, such as some of the reduction mechanism that you would need to use in soil, such as the distribution of the soil mercury concentration and organic concentration in soil, that kind of parameters. That we comment on those parameters?
Yeah. Those parameters certainly will affect the soil emission. At the present stage, I could only choose the soil emission based on the location of those sites and the historical deposition value from the literature. Let's say we have CMAC or OMICS, they produce the deposition amount, or we have a wet deposition map. We know which region has higher deposition. Apparently, those regions that those locations that have higher deposition, the soil content we assume will be higher. So the emission potential, we would choose the higher end value. For the remote areas, we would choose the low end value. But all those values should be within the range of the published values. That's the only thing we could do with our very limited knowledge on this topic.